Hey everybody, it's Mr. Duffy. Welcome to our physics lesson for today, which is about forces and the laws of motion. Specifically, we're going to be talking about what forces are, and we're going to learn how it applies to the first law of motion, which is the law of inertia. So go ahead and get started. Okay, so the first thing I would ask in this class would be, what would you describe a force as? What is a force? And again, we got a lot of different answers from you guys, but for the most part, we normally come to the answer of a force is something we would call a push or a pull. So again, pushing or pulling on something is again a good example of a force. Now, it doesn't have to be like an actual physical object. It could be like a field force like gravity or magnetism. Those are good examples of pushes or pulls, but you can't really see like what's pushing or pulling, but they're still pushes or pulls, which would be forces. Forces can change motion. They don't always. We'll learn about that later on, like what causes them to change their motion, but they have the ability to change an object's motion. The unit for force is named after famous scientist Isaac Newton, so we call it a Newton. It has the abbreviation of capital N, but really, again, that's just representing something else. A Newton is a kilogram times meter divided by second squared. So even though it's abbreviated Newton, which you'll see most of the time, it actually is a kilogram meter per second squared. And it is a vector quantity because it has a magnitude and a direction. So that is what a force is. Now, let's specifically talk about Newton's first law of motion, which is called the law of inertia. So here's what Isaac Newton said. There's a picture of him, and he published this and several other laws of motion in his famous book, The Mathematical Principles of Natural Philosophy, or Principia is what it's sometimes called. And the first law of motion that he described was every object preserves in a state of rest or uniform motion with constant velocity unless it is compelled to change by a net external force. Now, that is kind of complicated. Basically, what is that saying? Every object stays at rest or uniform motion, constant velocity, unless it's going to change because of a net external force. Well, basically that means things keep doing what they're doing unless you apply a force to them. So if something's at rest, it's going to stay at rest. That's kind of like a common way to say it. Something's at rest, something's going to stay at rest. And if something's in motion, it's going to stay in motion unless you apply a force to it. Okay, a net external force. Okay, and so objects just keep doing what they're doing. That's the concept with Newton's first law. Now, he gave the tendency of an object to stay, like to keep doing what it's doing. He gave it the name inertia, and so that's why we call it the law of inertia. It's the tendency of a body to keep doing what it's doing. So, inertia is really just a measure of the object's mass. So the more mass, I'll show you this in a later slide, but the more mass an object has, the more inertia it has. So again, the tendency of an object to keep doing what it's doing, if again it's a very large mass object, it has a lot of inertia, it wants to keep doing what it's doing more than something that's lower massed objects. Okay, but still, anyways, no matter what the case is, if a net external force is applied to an object, then and it causes the if there is a net external force on it and it causes the object to change its motion, again, it can happen. So if the net external forces are zero, though, the object's going to keep doing what it's doing. So a net force of zero, basically, that means that the sum of the forces is going to add up to zero. Basically, it just means we have like force one, force two, force three. These all add up. And again, if they all add up and they cancel each other out, the object's going to keep doing what it's doing. So here I have four forces on a car. We have a forward force from the engine. We have gravity pulling it down. The ground on the car pushing back up. We have air resistance backwards. So this is called a free body diagram or an FBD. We'll learn how to draw those tomorrow. But anyways, If all these forces again cancel each other out, then the net force equals 0. So the sum of the forces equals 0. And so that object's just going to keep doing what it's doing. And so, like, again, will its motion be like? Well, depends what it was doing initially. A lot of people would just say it's going to just stay at rest. And that could be an answer. If it was at rest initially, it's just going to stay at rest. But if it's moving, which I think likely it is, then it's just going to keep moving at a constant velocity. So that's more likely what's going to happen there, because it's like it's got its cruise control on. Now, I know more likely that it's moving at a constant velocity because it has some forward force there from the engine, as noted by the diagram, and some air resistance force there. So again, it kind of means that it's definitely, moving, and it's just not changing its motion. So like I said before, mass is a measure of inertia. More mass, more inertia; less mass, less inertia. So heavier objects, again, require more force. It's kind of, they resist the change in motion a little bit more than lighter objects do. So again, mass is a measure of inertia, and heavier objects are more resistant to that change in motion. Now, the law of inertia brings up a lot of cool examples, cool fun demonstrations.
How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And I should say, how do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is the subject of inertia. And I must make the matter, the idea clear, as follows. Here we have a block of wood at rest on the tabletop. And I ask, what does that block want to do? Answer, the block wishes to remain at rest. Supposing now I have double as much block, and I try in turn to put that system in motion, what do I discover? It also wishes to remain at rest. Moreover, it wishes to remain at rest twice as much, and therefore we say its inertia is twice as great. And so you discover at once that I have used the term inertia and referred to the idea of mass as synonymous. So mass and inertia are synonymous. And this is all tied up beautifully in Newton's first law, which says what? If a body is at rest, it wishes to remain at rest. And if it is moving uniformly in a straight line, that's what it wants to do. In English, simply, whatever a body is doing, that's what it wants to do. Let's look at Newton's Latin for it. Newton put it in Latin. Axiomata sive legis motus. Axioms, even laws of motion. Corpus omne perseverare in statu suo quiescendi, and so on. And in English, a little more within our competence. Every body continues in its state of rest or of uniform motion in a straight line, unless there are some forces to divert it. Consider now the following. Here you come on April Fool's Day, let us say, on a package, on two packages resting on the ground. Here is one and here is another. And you deliver, you impose a force on the one. I will, instead of with my foot, with my hand, and it experienced such a motion. The force produced a motion in the body of so much inertia. Now I try it with this one. Hardly as much motion. Why? This one is filled with rags, and this one with 2 bricks. And this one has the greater inertia. So, the measure of the mass of a body is its inertia. Consider now the 2 aspects of Newton's first law. A body at rest wishes to remain so. Here I have a heavy block of wood, a hole in it, and I put a dowel rod in the hole. The dowel rod constitutes the handle. How can I put that handle into the block? As follows. As follows. Notice what happens. I hit the handle. The block remains at rest, whereupon the handle moves into the block. That's the first law. The body of large inertia wishes to remain at rest. Let me pursue this in another way to demonstrate the second part of Newton's law. What did the second part say? If the body is in uniform motion in a straight line, that's what it wants to do. I start again. Now I come down on a firm block. The motion of the handle is arrested. The handle and the block were moving. And what does the block want to do? Keep moving. Whereupon it lodges itself more firmly on the handle. Thus do we demonstrate Newton's first law in two parts. Let me do this another way. Very pretty. Very pretty. I have a support and a weight W supported by a string and another string with a loop in it here, which I shall show you. Let me call this string A and this string B. I propose to do as follows. I'm going to pull on string B, the lower string. And I can break either string B or string A by invoking Newton's first law. If I pull suddenly on string B, W wishes to remain at rest, and B will break. On the other hand, if I pull gently on B, A supports W, already there, plus the force I impose. And I shall show you that exactly with this demonstration. Here is a string. Here is a hook. Here is a weight. And the upper string is supporting the load. Here is the lower string, and I am putting a little rod inside here so that my hand is not underneath should the weight fall. I am going to break the lower string. Watch it now, the lower one. There it is. I broke it. Now I am going to change the string. I'm going to change the string. And now I am going to break the upper string by pulling slowly on the lower one. Watch it now. Watch. We hope that breaks. Now, supposing it does not. One is led to say the experiment has failed. And I say, no, the experiment doesn't fail. I have failed to meet the requirements of nature. Watch. I'm going to break the upper string. There it is. And so we can be applauded for success. Consider another demonstration of the same. Here is an enormous weight, 16 pounds. Here is a string attached to it. If I pull on that string in a gentle way, I'll do it by hand, in a gentle way, the string can support the load. Now let me try to accelerate it. What does Newton's first law say? Body wants to remain at rest. It has enormous inertia. Watch it. Do you see? The string has broken. I shall have more to say about this when I talk about Newton's second law. The second law. Consider now another dramatic demonstration. An application of Newton's first law, because we must not escape the fact that these laws of physics, of nature, of science, have vast applications in plebeian things. A brick, a trowel. Cannot the craftsman, the bricklayer, utilize Newton's first law in this way? Notice if he hit his hand with the trowel, he'd hurt it. But he can hit the brick with absolute abandon and feel nothing.